We've now seen how the select operator can be used to retrieve data either from single tables or from multiple tables using joins. This gives us a lot of power. The real power comes from combining select statements together to form complex queries. Let's see how this is done. The result of any select statement is a database table, like any other, which represents a relation, which means that just as in relational algebra, we can take the result of select or project operations within relational algebra and combine them using set operations, we can take the result of select statements and also combine them using set operations, and these set operations are provided to us within SQL. We have union, we have intersect, and we have except, which represents set difference, also sometimes called minus. Now, there's a slight difference between the theoretical model of relational algebra and how it's implemented in SQL. In SQL, a database table, despite the fact that it represents a relation, and a relation is a set, a table can, in principle, contain duplicates. So if the result of a select statement might result in duplicates, we may or may not want to remove the duplicates. There are some cases in which we want to keep all the duplicates and then deal with them in some fashion. So for set operations, the pure set operation is indicated by the keyword, which is the name of the operation, union, intersect, and so forth. If you want to make sure that duplicates, if any, are retained, you can say, for example, union all, which means that if both sets contain the same tuple, it will be retained in the result of the union. This can be done in SQL. And this is the case for all of the different set operations. So let's see how these set operations can be used. Suppose that we want to find the name of all customers who either live in the United States or in Canada. Well, one way to do that would be with a disjunctive condition to say, select customer name from customers where country equals US or country equals Canada. Another way to do this, however, would be to use a union. Select the customers where the country is the United States. Union, select customers where country equals Canada. And this is all one single statement in SQL. Two selects, union, another select. So we're going to find all customers in either US or Canada and remove all of the duplicates. Now, suppose we want to find customers in either the US or Canada, and if that customer is in both the US and Canada, we'd like them to appear twice in the output list. So we see that there's a duplicate. Here we say union all. In this case, we will retain all of the duplicate customer IDs and customer names from both selects. Those customers will appear twice if they come from both lists. Now suppose we wrote the following query. Select customer ID, customer name from customers where the country is US. But in the case of the Canadian customers, we select customer ID, customer name, and country. So the first select has a schema that only has two attributes, customer ID and customer name. The second select is going to return a table with a schema that has three attributes, customer ID, customer name, and country. What happens if we do this union? Well, if it was purely a set, we just get a set where some of the rows have two attributes and some of the rows have three attributes. However, we can never have a table whose rows have different numbers of attributes. A table, like a relation, has a defined set of attributes, which means you can't do it. If the selects have different schemas in their output, you cannot perform a set operation between them. The schemas have to match, and that is the case for all set operations, union, intersect, what have you. Now, suppose we want to find all of the customers who are both in the US and in Canada. Well, in that case, we can use an intersection. So we say select customers from the US, intersect customers from Canada. We will find all pairs of customer ID, customer name that appear both with the country of the US and with the country of Canada. So we'll get all of the customers that operate in both countries. Finally, now suppose we want to find all of the customers who only are operating in the US. We can use the except keyword, which gives us set difference. Find all the customers with the country equal to US, except the customers where the country equals Canada, which will give us only those customers in the US whose customer ID and customer name do not appear with the country equal to Canada as well. So all the customers operate in the US, but not in Canada. There are other useful operations that we can also do here. So often we'd like to test whether any results are returned from a select statement. Are there any customers that have a loan? I'd like to find all the customers who have at least one loan. I could do that using a join, but that might be expensive. If some customers have a lot of loans, I might have to retrieve a lot of data, which I don't really care about. All I care about is there at least one loan? So I can say explicitly, select customers where exists with a nested select statement. And notice the parentheses. We can put parentheses around the select statements wherever you want. It gives you the same answer, just helps to know what the grouping of the expressions is. Where exists, select from loans where the customer ID equals a loans customer ID. So we're in effect doing this join, but all we're doing is testing whether there's any record in the loans table that matches that customer ID. That's all we need to do. This will find all the customers that have at least one loan. Notice that we have a nested query here. We're putting a query inside of another query. This is an extremely powerful technique in SQL, which allows us to use intermediate results to compute and to do other kinds of queries. You have to be careful, though, because sometimes you can take an efficiency hit. It can sometimes get very expensive if you're not clever about how you do that. In the same way, we can test whether any result exists, whether any result was returned from a select. We can test whether no result was returned. So if we want to find all of the customers that have no loans, we can similarly say select customer name from customers where not exists, select equivalent data from the loans. In this case, if no loans exist for that customer, that condition will return true and that customer will be selected. But if any loans exist, that customer will not be selected. Another type of condition that is often very useful is the result unique? And we can test that using the specific keyword unique. We can select all products in our product list, which are only sold by a single vendor. And one way to do this is to say, select the products where unique the result of looking for the vendor. So if there's only one vendor, it will say true, so we'll get that product. If there are 0 vendors, or if there are 3 or 5 or 100, the condition will not be satisfied and we will not see that product. We'll only see products that have exactly one vendor. And by the same token, we can also select for products that do not have a unique vendor by appending the keyword not, where not unique gives us all of the products who do not have a unique vendor, just as you might expect. Diving a little bit deeper into comparisons and thinking about sets within comparisons, we can do comparison of some attribute value with every value from a particular set. Suppose we want to find the employee or employees that have the highest salary in the company. We'd like to select the employees where their salary is greater than or equal to every other salary in the company. We could do this by joining the employee table with itself and comparing every salary to every other salary. Or we can specify where salary is greater than or equal to all of the result of selecting salary from all of the employees. Now, by telling the RDBMS that what we're trying to do here is not just a join between all of the data points in the employees table with all the data points in the employees table, but telling it explicitly, what we're trying to do is find a salary that is greater than or equal to all of the other salaries. The RDBMS can then apply optimizations to this query, and it can be executed potentially much faster than doing the full join. We're giving it a hint as to what we're trying to do to help it to optimize. In addition, we get code that may be more readable than the other version. Now, if we combine set comparison with aggregation, we can do some really cool stuff. We have an employee projects table that lists every employee with all of the projects that they work on. So for any given employee, I can count the number of projects by saying group by employee and figure out the count of the employee within each group. So the number of times the employee appears in the employee projects table, or the number of projects that employee is working on. So I can say, select employee IDs from the employee projects, group by the employee ID, and with the condition of having the count of employee ID, the number of projects that employee is working on, be greater than or equal to all, again, of selecting the count of project IDs from the employee projects, grouping by the employee ID. So we count the projects for all the employees in the nested query and require that the count of the employees in the outer aggregation be greater than or equal to any of those values. So here we're going to get the list of all the employees working on the most projects. In the same way that we can use all to look at every value in the set and require some comparison, greater than everything in the set, less than everything in the set, or something like that, we can also specify that we want a condition to apply to some, at least one of the items in the set. And we use the keyword some to do this. So suppose we want to find, instead of the employees that work on the most projects, we want to find the employees that work on more projects than at least somebody. We can do this by simply replacing the keyword all in the last example with the keyword some. Here we're saying the count of employee ID has to be greater than some of the counts in the nested query. So that every employee that is returned will have more projects in the employee projects table than at least someone else. Nesting select statements, as you can see, gives us tremendous power to be able to compare not just one data item with another data item, but data items with whole slews of data items. Now we're about to see some of the real power of using nested queries. Remember, the result of a select statement is a database table. Even if it's not represented explicitly in the database, we don't remember it after we've executed the query, it doesn't have its own name, it's a database table. If I can select something from a named database table, I should also be able to select something from the result of another selection. So we can nest select inside of from to get even more power. So suppose I want to get all of my customers and I want to know the average loan amount for each customer. That requires me to join the customers together with the loans table. Well, I can do that join within a nested query and then select from that result to get the averages that I need. So the nested query says, select customers, customer name, and loans amount from the join of customers with the loans. And I'm going to rename loans amount to loan amount in the result. So now I have a intermediate temporary table with two fields, customer name and loan amount. I can then say, select the customer name and the average loan amount from that intermediate table, and I'm going to get the kind of result that I want. I'll get the average loan amount for each customer, no matter how many loans they have. In conclusion, the fundamental select operation can be combined in multiple ways to create complex queries that do complex information processing within a single SQL statement. Set operations of various kinds allow combining and comparing different result sets or comparing particular data items to everything in a result set. And by putting subqueries within the from clause, we can create intermediate tables that then allow us to do much more complex calculations within an SQL query. In the exercises, you'll see many more examples of this. Work at them, practice them, become comfortable and smooth with building queries and building complex queries. As you become more familiar, you'll be able more and more to realize the true power of SQL to work with your data effectively.